thank you very much for your continued attention tonight. And as you said, we've really spanned the gamut here at TED from souls and bodies now to the universe. And there's even a connection to that wonderful seed talk we saw earlier, because one of the things I'm going to be talking about tonight is the seeds for the first galaxies and stars to form in the universe, and more to the point, our search for those seeds. This is one of the deepest images of the sky ever taken. This is the so-called Space Telescope Hubble Deep Field. This is about 1 million seconds of exposure time. That's over 11 days of exposure of this telescope in orbit around the Earth, adding images together to produce this very, very deep image of the sky. If you want to imagine how much of the sky this is, you can imagine taking 1 millimeter by 1 millimeter square and holding it at arm's length up against the sky. And this field in particular was chosen to be a blank field prior to this imaging. So what you see here, revealed, are literally 10,000 galaxies that were previously unknown before this image was taken. And if you go even deeper than this, people have actually doubled now the exposure time of such an image. You get many, many more. And in fact, there are some galaxies that are seen today that are 1/10,000,000th faint as the human eye can see. So we are pushing further and further back into time, into the universe, and I'd like to tell you a little bit more about our search for how those first structures form. If you actually investigate, say, a portion of this image, blow it up a little bit, zoom in, move across it, that's what this inset shows you at the bottom, you can see the brilliant diversity of galaxies. And in fact, the furthest galaxies that you can see in this image, many of which are the dimmest galaxies you can see in this image, tend to date back from only 500 million years after the universe formed. And as we know now, the universe is about 13.7 billion years old. But the thing I want you to recognize is the diversity of the galaxies. We don't understand how that arises. We don't understand how galaxies get their stuff in detail. And I can tell you that as far back as we've pushed in this image, there are still more galaxies undoubtedly lurking beyond what we have seen. And the question is, what now? We've taken the deepest possible images we can. We've used many of the most sophisticated telescopes in the world, not only the Hubble Space Telescope, which you can see over to the right, but telescopes like those in Arizona. That's the Large Binocular Telescope, run in part by the University of Arizona. That's here in Mount Graham, about 3 hours east of here. This is one of the most technologically sophisticated and largest telescopes in the world. And we are doing amazing things with it. This is very much a Renaissance period in astronomical history, and yet we still can't see galaxies earlier in time than about 500 million years after the Big Bang. And we still haven't pushed to that point which simulations, which theoretical models tell us, where galaxies are fragments of their later selves, collapsing from their own gravity and forming. So how do we do that? If we struggled with these heroic Herculean efforts to detect galaxies, at this point, we're pretty much down to this: a handful of candidate detections of galaxies in the furthest reaches of the universe and at the earliest times. Literally a handful, and they don't look that good. This is artist license here. Actually, they look like pretty nondescript blobs to us that are barely resolvable. So is it possible to do better? And I can tell you that there are tricks you can play. There are opportunities provided by nature that one can utilize to their advantage. And one of them comes from Einstein's theory of general relativity. Let me explain a little bit what I mean by that. Let's say that there were a cosmic lens, a lens through the distribution of mass in space, that before the light even reaches the Earth and reaches our man-made telescopes, focuses the light of distant sources and helps us see things that would otherwise be too faint to detect. The idea is very much like taking a magnifying glass to a part of the sky, like that beautiful spiral galaxy zoomed in on that I showed you earlier. actually that's in some ways very similar to our own Milky Way. How is this possible? Well, general relativity tells us that mass in space bends the space. So you can imagine what is very much an artistic conception at this point, a rich cluster of galaxies, a compendium of thousands of galaxies all orbiting one another, experiencing their own gravity and the dark matter that binds the system together. In space, the space that's represented by this bent grid here, that cluster of galaxies puts a dent. That's what general relativity says, mass bends space. And the other thing that we know is no matter what space does, light paths must follow. So if you imagine what would have to happen to a light ray that would otherwise go about its business in a straight direction in this space, in the presence of this space-bending mass, it would be diverted. Its path would be bent, very much like a lens. And this is a system called a gravitational lens, and they really exist. Let's look at it another way for a moment. So this is another picture of the concept that I just showed you. If you take a look in the middle, you can see that rich cluster of galaxies again that has so much mass that it puts a big dent in space. And you can even make out the dent that it's putting in the space. If you imagine for a moment that we're down there at Earth, on the lower right, and we want to observe a distant galaxy that's up in the upper left, well, we're so far away from that galaxy, even though that galaxy is emitting light in all directions where it is, only a very, very small fraction of that light is lined up with us in such a way that we could detect it. That makes the galaxy faint to us, makes it hard to detect. But one might imagine putting a lens, like a cluster of galaxies, in between us and that distant galaxy. What happens then? Well, the same amount of light as before would get through to us, but in addition to that, some of the light that would otherwise gone out in other directions gets bent by the bent space in our direction. And you can see that happening here with some of those light rays. So this is a nature-made way of magnifying that distant galaxy and perhaps making it detectable. But there's a problem. And the problem is the following. Even though that magnification of that foreground lens brightens the distant galaxy that we want to see, perhaps the earliest galaxy ever, it also zooms in to that distant region of space. So if there are very few galaxies out there to detect, and you're only looking at a tiny portion of that distant space, your chances of detecting one drop. It's a bit of a catch-22. So the question is, can we work around that catch-22? Maybe not eliminate it, but improve upon the situation. And here's an idea of how to do that. Let's say we made our lens much more complex. Let's imagine for a moment that there are places in the universe, directions on the sky, where not just one rich cluster of galaxy provides a gravitational lens to a distant galaxy, but that there are several stacked up along the line of sight. Well, what happens is that changes the shape of our gravitational lens. And it may make it possible, you see that additional galaxy in the upper left now? It may make it possible to take the light emitted by that distant galaxy and bend it in line with the Earth. So now, instead of just bending the light of that one galaxy and brightening it, we're bending the light of two. What if we make our gravitational lens even more complex by adding more mass along the line of sight? Something like this, for example. Then another galaxy's light could be bent in our direction. So conceptually, it's possible to sample more of the distant universe and increase our chances of seeing more galaxies brightened up to the point where we can detect them. And the next obvious question is, do these things really exist? I just waved my hands and showed you a cartoon. Here's another representation, but this is actual data, of the universe. The Earth in this picture would be at the bottom, at the vertex. And we're looking outward into the universe at the distribution of galaxies along a strip on the sky. So as you move outward along the pie slice, you're going deeper and deeper into the universe, and you're seeing a slice of it. Everything yellow in this picture is a galaxy that has been mapped, and this is a slice through a 3D representation of that. And what I want you to imagine is that there are directions on the sky that we can look towards from that point at the bottom, outward and beyond to the distant universe, that might help magnify it into detectability. There are directions in this map. Here's one, for example, that has a lot of galaxies clumped together along the line of sight. A lot of lensing capability, and if those lenses are in the right places with the right configurations, then maybe they give us an edge over our man-made telescopes. Here's another line of sight. You might begin to imagine that this one might even be more advantageous for lensing. There's a lot more mass that has been captured in this beam towards the distant universe. So I'm going to end with showing you an actual one of these special directions. We've now identified about 200 in the sky, most of which people have never looked at before with this question in their mind. And they're all we'll ever have until we get a collaborator in another galaxy that has different directions he, she, or it could look through. So this last picture has a lot of galaxies in it, just like the earlier images that I showed you. It's not as deep, but it's filled with gravitational lenses. Every object that you see in this picture is a galaxy that's associated with some cluster, and there are about 5 different clusters all concentrated on this part of the sky, all providing gravitational lensing to the most distant galaxies. So please stay tuned. We've just started mapping these regions and understanding them, and we plan to follow up and find the earliest forming galaxies. Thank you.